Okie doke. Now that the technology is fixed, good morning, everybody. Yesterday we got to start by looking into some very useful units in relativistic field and quantum field theory, and also we had a brief recap of four vectors. But now let us really proceed to the topic of the lecture. So let us really go to in a way an introduction to field theory. And as I already mentioned yesterday, the idea is really to start with classical field theory. And first of all, this is very useful because in quantum field theory, you typically start with a classical field theory and quantize it. That's like in ordinary quantum mechanics, you start with a mechanical system like an harmonic oscillator, and then you quantize it. And the same is true in quantum field theory. You start from a classical field theory and then go to quantum field theory. So start field theory and then go to quantum field theory. Apparently it doesn't really work. Okay. But there's also another reason for going from classical field theory. If you remember from quantum mechanics, there is something like the Ehrenfest theorem of quantum mechanics, which tells you that the expectation values of quantum mechanical operators follow to some degree the equations of motion for classical fields. And there is something similar in quantum field theory. In quantum field theory, we can typically get something like, if you want, modified classical, should say something like this, modified classical equations of motion. So basically, these modified classical equations of motion for the expectation values now it's really embarrassing. Oops. Sorry about that. So the idea is quite often that in quantum field theory you calculate something called the effective action, from which you then derive classical equations of motion, which describe the behavior of the expectation values of the quantum field. So basically you get more or less, they're a bit modified. That's the hard work in quantum field theory, to calculate the modifications if you want. But then you can take this more or less classical field theory and calculate the dynamics of the expectation value of the quantum fields. So after you've calculated something like a so-called effective action, you can treat it to some degree as you would a classical field theory. And that's, for example, something in particular the cosmologists very often do when they write down classical equations of motion, they quite often implicitly assume that they have calculated something called an effective action, and then all their fields are actually expectation values of quantum fields. So the expectation values, to some degree, behave. It's not true to all details, but to some degree they behave like classical fields. That's why classical field theory is also very useful when dealing with quantum field theory. So to get started, let us now do a brief recap of Lagrangian and Hamiltonian. There are basically two approaches to classical field theory, or also to classical mechanics, and that's typically the Lagrangian and the Hamiltonian approach. You've probably seen it, but let me just very briefly recap it. So in classical mechanics, we have the Lagrangian which is given basically it's a function that describes the kinetic energy and which depends on the coordinates and the time derivative of the coordinates. The dot denotes the time derivative. And a potential energy, and it's minus the potential energy. And typically, this potential energy is not dependent on the time derivative of the spatial coordinates. That's a simplification. It's a conservative system, so not dependent on q dot. It's a conservative system. And the q's here and the q dots are the generalized coordinates. So here we have generalized coordinates. So from this Lagrangian function, which is really a function of these generalized coordinates and their time derivatives, we then have the equations of motion, which are the Euler-Lagrange equations. And which are simply given by the total time derivative, the partial derivative of this Lagrange function with respect to the generalized velocity, so to speak. And of course, we can have lots of them. We can have lots of coordinates, so we can have lots of velocities, minus the partial derivative with respect to the spatial coordinates. And this, to be an equation, of course, should have a right-hand side, and the right-hand side is simply 0. You can also briefly check, just to remind you that this is good physical practice, that the units of these two terms are actually the same. So here we have some function which should have units of energy with a derivative with respect to spatial coordinates. So that is something divided, so to speak, by a length. And here we have something divided by a velocity, and the velocity is length per time. So it's something times time divided by length, and the time derivative takes care of the times time. So the overall thing is again something divided by a length. So both of these terms have the same units or mass dimension. What is the advantage of this Lagrangian? Well, one simple advantage lies in the fact that these are generalized coordinates. The point is simply we can choose whatever coordinates we like. So we are not restricted to writing down everything first in Cartesian coordinates and then translate with quite some tedious work the equations of motion into some different coordinates, but we can directly write down this Lagrange function in terms of our more suitable coordinates that we have chosen. And the Lagrangian reflects directly the symmetries of the system. That means it is invariant under symmetries. There's a slight generalization to this statement of invariance later. It's actually not the Lagrangian, but so a thing that we'll call the action that is invariant. Okay, so to see these advantages of the Lagrangian approach, let us briefly take a look at an example. Raise a little bit first. Okay, so let us look at an example, and it's really a very simple mechanical example. It's the harmonic oscillator in 2 dimensions, in 2D. So let us basically start with the coordinates. Well, if we have a harmonic oscillator which in 2 dimensions, which is rotationally invariant, basically, which looks the same in all directions, in the x direction and the y direction, it's very useful to choose something like polar coordinates. So we say x is r times sine of phi, and y is r times cosine of phi. Now, our Lagrangian, just to make it physically explicit, is the kinetic energy minus the potential energy. So we can easily write down the kinetic energy in Cartesian coordinates. That's 1/2 m velocity in x direction squared plus velocity in y direction squared. That's just Pythagoras. And then we have our potential energy, which for a harmonic oscillator is nothing but the spring constant by a suitable normalization times r squared. Because the potential just depends on how far you are away from the origin. Now we would like to re-express that kinetic energy in terms of our generalized coordinates. So we simply say x dot is equal r dot sine phi plus phi dot cosine phi times r and y dot r dot. Okay. Now, I'll save you the tedious calculation of adding these two together, but you see that the result is actually quite simple. Putting that in, we find that our Lagrangian is actually 1/2 times the mass times r dot squared plus phi dot squared times r squared minus 1/2 k squared. And the sines and the cosines all have gone away. They have simply added by sine squared plus cosine squared to 1. What can we notice on this Lagrangian over here? Well, it does, for example, not explicitly depend on phi. It just depends on phi dot. So there's no direct dependence on phi. And this no direct dependence on phi is the fact that this system is rotationally invariant. You can rotate it, and it looks the same in all directions. And therefore, the Lagrangian shouldn't depend on phi. So it's independent of phi, and we treat phi and phi dot in a way as independent variables. So it's not dependent on phi, but it depends on phi dot. And that is the effect that the rotation symmetry is implemented. Okay. Now, we can do our equations of motion, and these will also show us the effect of this rotation symmetry. Let us first look at the equation for phi. So we have d by dt, dl by d phi dot minus dl by d phi. So this thing here is 0 because L does not depend on phi. So we have just d dt, and the derivative with respect to phi dot simply gives us the 2. So we have m phi dot r squared and nothing else, because that is 0. And before I write the 0 on the right-hand side, which I can put here, what is m phi dot r squared? Well, that is, any ideas? Exactly. This is d dt. And now I need to make some different L. I'll give it simply an index. So this is angular momentum. So basically, the independence of phi automatically gives us the conservation of angular momentum, which is conserved. Therefore, the only non-trivial equation of motion, in a way, is the one with respect to r. And that's d dt, dl by dr dot minus dl r is equal can simply plug it in. This first term minus m phi dot squared times r plus, and here the potential term, of course, plays a role as well, and this is equal to 0. And if we write that in a slightly more explicit form, we find that m r dot dot is equal to m phi dot squared times r minus k times r. And if you want, you can view this as an acceleration, and the right-hand side should then be a force, and that's simply the centrifugal force, and that's the force by the oscillator. Okay, so with this explicit example, you see how concisely you can condense all the properties of the system into this Lagrange function, and how you then, by writing down the equation of motions and studying the properties of this Lagrange function, you can actually see all the properties of the system, like the fact that the angular momentum is conserved. If you want to practice that a little bit, on the exercise sheet I handed out yesterday, there's also another example of a mechanical system which can be easily dealt with by using the Lagrange formalism with this ball on a rotating stick. Now, the question is, what is behind these Euler-Lagrange equations? Well, the Euler-Lagrange equations originate from the Hamiltonian principle. Which is that we have a thing called the action, which is, and we'll come to the definition of this word in a second, which is a functional, most of the time it's called S, which is a functional of the generalized coordinates and their time dependence. It's really the time-dependent functions that go into this functional. So it's really the function of time that goes into the argument of this functional. And what is this functional? It's an integral from one time to another, which are basically the starting and finishing points of your motion. It's a time integral of the Lagrange function. Now I make it explicit that these are functions of the time. So the generalized coordinates are functions of time, and of course also the time derivatives are functions of time. And the Hamiltonian principle says the action is stationary along the path. So whatever path your your mechanical particle takes, the action is stationary at this point. And stationary means that the path is an extremum of the action. So the path that is actually taken by the mechanical particle is an extremum of this functional. That means that if you go a little bit away from this path, if you deform the path a little bit, this action functional typically increases in all directions for this modification. So if it's a minimum, it increases in all directions. If it's a maximum, it decreases, but it increases only in second order. It's like if you are on a maximum of a function, if you're sitting here, if you move a little bit away from it, it always decreases. But it's always kind of a small, very small effect. It's a quadratic effect in your deviation from the maximum. So at lowest order, if you move a little bit away, it actually doesn't change at all. And that's where the stationary comes in. And the same goes for minimum. The first derivative is 0. And we'll learn what the first derivative of this action function is in a second. This is quite a fundamental principle. So this is basically going from writing down some Euler-Lagrange equation, which is a differential equation. It's going to an extremization problem. You maximize or minimize a certain functional. And that's basically the nice thing about the Hamiltonian principle. And just to take a really big step ahead, and you'll probably hear more about that in the next part of the quantum field theory course, basically in 4 weeks or so. This thing also leads to the kind of the fact that big objects behave classical, where small objects behave more quantum mechanically. The idea is basically, in quantum mechanics, let's start differently. In mechanics, you're really sitting here, or you're really sitting here. So you're really sitting in the extremum in classical mechanics. So you really take the extremal path. In quantum mechanics, you in a way take all paths. So you also take a path that has an action that is a little bit higher, for example, that is away from the minimum. But going away from this minimum, there's a punishment, so to speak. This path is less likely. So a path over here that deviates from the minimum is less likely than a path that is very close to the minimum. Now, the difference between a small and a big object is simply, well, for a small object, you would have something, say, like this, where your minimum is somewhere over here. It's relatively wide and slowly changing minimum. So to speak, the minimal valley is rather shallow. It's rather wide. So even a path over here or a path over here are OK and contribute to some degree to the quantum mechanical evolution. But say if you throw a macroscopic object, macroscopic ball, it looks, and that's a crude understatement, it looks something like this. So even if you move a little bit away from the classical path, the punishment and the lower probability really strikes you. So going a little bit away from the classical path is extremely unlikely for a big object. So basically, if you want to look at our action here, the thing that dominates it is this mass, in a way, and the typical length scales of the system. If the mass is big, the Lagrange function and the action function are huge. If the mass is small and the object is small, then this action function is also small. Basically, multiplying by an overall number changes from here to here. And that makes a difference between classical and quantum behavior. OK, before we go into a little bit more detail about the idea of a functional, let us also briefly recapitulate the other way to describe mechanics, which is the Hamiltonian approach. So let me erase it a little. We can also do Hamiltonian mechanics. And, well, unsurprisingly enough, Hamiltonian mechanics is based on the Hamilton function. And this Hamilton function is now a function, again, of our generalized coordinates. But instead of being a function of the velocities, of the generalized velocities, it's a function of something which we would like to call generalized momenta. And it can, of course, also depend explicitly on time, but we'll usually neglect this time dependence. And how is it defined? It's simply the sum over all these coordinates pi qi dot minus the Lagrange function. So it's directly connected to the Lagrange function. But the important point is, in the Lagrange function, and also here, the important point is to replace all these velocities by these momenta. By the momenta. And of course, to do that, we need to know what the momenta actually are. And the momenta are actually the derivatives of the Lagrangian with respect to the velocity of the appropriate generalized coordinate. So this side is really a function of q and p. And that means that here we have to express all the qi dots by pi and qi using this formula over here. So this side does not explicitly depend on the velocity. Now, to the physical interpretation, the Lagrangian was the kinetic energy minus the potential energy. And for the Hamiltonian, we have something similar, something even more physical, at least in conservative systems. So again, our constraint of conservative. So in conservative systems. And technically, there is also another constraint with time-independent constraints. A constraint is something like, for example, that your particle is attached to a string and cannot move further away from a certain center than the length of the string. If that is true, then the Hamiltonian is actually equal to the kinetic energy plus the potential energy. So it's actually the energy. And that is something you probably have already used to some degree in quantum mechanics when writing down the Hamiltonian. That's where one usually learns more about the Hamiltonian. Okay, having this Hamiltonian, we have already seen that it is directly related to the Lagrangian, and that's something you can check for yourself. This transformation here is a Legendre transformation of the Lagrangian. So that is a Legendre transformation. And just as background knowledge, it would be good if you familiarize yourself with the idea of a Legendre transformation and maybe try out that this is indeed a Legendre transformation of the Lagrangian. To conclude, let us look at the equations of motion in Hamiltonian mechanics. The equations of motion are, again, given basically in form of time derivatives of certain coordinates and partial derivatives of the Hamiltonian function. So it's the velocity, generalized velocity, is the partial derivative with respect to the momentum, and the time derivative of the momentum is the negative partial derivative with respect to the coordinates. And in principle, if you have a time dependence, you can have something like dH by dt. But this only if L explicitly time dependent. So instead of having one Euler-Lagrange equation, which was, however, typically second order, as we have seen in the example, it was an equation which contained two time derivatives, we now have two first order equations in Hamiltonian mechanics. Okay. Oops. There we go. Okay, so let me see. Let me erase this part over here. In particular, for this action, we have already briefly encountered the idea of a functional. And that is something very useful in field theory and also in quantum field theory. So let us take a brief look at functional. So let us look at a mathematical tool. So let's take a brief detour into mathematics. Into functionals and functional derivatives. And functional derivatives. Okay, so I've thrown around the word, so let us first see what a functional actually is. A functional is a map of a vector space V, which lives over the field F. That means each vector can be multiplied by numbers out of this field F. Typically, these are the real or the complex numbers. And this map goes to F. So the functional F is actually a map from the vector space to the accompanying field F. So we can do a very simple example. It's something we usually wouldn't even call a functional, but a very simple example is actually taking the vector space to be the real numbers to some power n, and take a vector in this vector space, in this Rn, and then we can define a functional from Rn to R, and which we can give very explicitly. We take any point x in Rn, and we simply take the scalar product with respect to y. So y is the other vector. It's a constant vector multiplying x with a scalar product. So that's the scalar product. And of course, this side over here, it being a scalar product, is a normal number. It's just a number again. So this thing over here is a very simple functional. So if we want to be very boring, we can actually say any function of Rn or Cn to R or C is actually a functional. It's not just a function, it's even a functional. So far, this whole thing doesn't seem to be very new and very exciting, but there are, of course, slightly more interesting functionals. And in particular, in physics, we are interested in a certain type of functionals. And that becomes interesting when this vector space is not just some n-dimensional real vector space, but typically, in physics, V is typically the space of functions. And the field is typically R or the complex numbers. So the important point is functions are typically mapped onto numbers. And that's exactly what we had in our action functional. We had this this function q of t, which was a function of the time, which was mapped by an integration onto a given number. So before we take a break, let us look at a small example to get warmed up of this type of functional. We have an example. Let us take the continuous functions. On an interval x1, x2. And then we can have a nice functional of the type, and that's, let me give this a name. So these continuous functions are typically called C of the appropriate interval. And then we can have a functional C of x1, x2. And if we take them to be real function, for example, we can map this onto R. And space here, we can simply define a very simple functional by saying, well, we simply integrate from x1 to x2 dx f of x. The right-hand side is a number, which, of course, depends on the function we put in here. So, for example, if we take the function, which is simply x, we get out a number simply by integrating x over the interval x1 to x2, which is 1/2 x2 squared minus x1 squared. So that is the general functional. So that is then the functional evaluated on the function, which is simply x. Similarly, we can evaluate the function on x squared, and that's, of course, a different number. The right-hand side is a fixed number because x2 and x1 are just normal numbers. They are fixed, so they are really entering this definition of the space over here. They are a fixed interval from x1 to x2. And if we do it here, we, of course, get something like this. We get a different number. So integration is therefore a very simple functional on the space of integrable, or in particular on the space of continuous function. But I stress here that we are talking about the definite integral, because only if we have a definite integral, what we obtain is actually a number. So the definite integral is a functional. But this is by far not the only functional we can have. Going from there, taking this integration, does anyone have a suggestion for another functional? I'll rub a little bit more and yeah, but yes, that's definitely a functional. But say of this type, let's put another functional on the same space of continuous functions. So just another functional that acts on this space of continuous functions. Very, very simple, small modification of the first one. What could we do, for example? We can.
Of a function of a function.
Yes, we could. So you want to do the integration of the function evaluated on itself.
Well, not necessarily that function, but any function of whatever.
Ah, exactly. So that's exactly the one I had in mind. So before we are so general, let's simply take an explicit function, which is, for example, a polynomial. For example, we could have a functional b of f, which is an integral dx f to some power of x. So or maybe I should be a little bit more careful and do it like this. So this is also a nice functional if we take n bigger than 0. We should do that to remain continuous. But you are absolutely right. We could, in principle, take, now I have to give it the proper name, we could take, so to speak, any function that is sufficiently nice. So that could be any function which is sufficiently nice, meaning also continuous. So we could take f of x squared plus 4. We could cube it. We could take even an exponential of f of x, and it still remains a function. So we still do integral x1, x2, dx. And as you already said, well, this is more or less, if we replace x by some time and f by our generalized coordinate, that already comes pretty close to how our action function or our Lagrangian looked. OK, I think maybe this is a good time to take a brief break, say 5 to 7 minutes, and then we'll encounter some more examples of functionals and what we can do with them.